Hello, Longhorns. Welcome to Lesson 6, the final lesson in your momentum chapter. Today we're going to look at elastic collisions. We've had a chance to investigate momentum, that is represented by the letter P. We looked at mass, represented by the variable m, velocity, which is v. We've even revisited force, capital F, and time, which is lowercase t. Now we're going to look at your equation that's actually pretty familiar. If you had a chance to watch the conservation of momentum video, this equation will look very, very familiar to you. So first things first, let's go ahead and define what is an elastic collision. A perfect example of an elastic collision is a set of bumper cars. Think about it. The word elastic kind of reminds you of a rubber band, something that I'm able to stretch, but that if I let go, it will also return back to its original shape. The same thing kind of happens here. You have two objects that are coming together. They have a collision, but in an elastic collision, they're going to separate and go in two opposite directions. The equation that we use to represent your elastic collisions is the same one from conservation of momentum. The mass and velocity of the first object, mass and velocity of the second object. This is your initial side that should be equal to what is on the final side. Let's take a look at a problem to see how this one works out. Now, you also remember that if you have an elastic collision where two objects come together, collide, and separate, the opposite is if I have an inelastic collision, because the prefix in means not or without. In an inelastic collision, I'm going to come together, stick together, and whomever had the most momentum, that's the direction that I will continue to move in. A good example is an accident between a car and a motorcycle. These two collided with one another. If the car continues to move, since they're now stuck, it will move in the direction of the car, since the car has more mass than the bike. The equation is easy for us to see this as well. Mass and velocity of your first object, mass and velocity of your second object. We have a collision take place. They're now stuck together. It's inelastic, and they're going to move at the same velocity with one another. All right? So, example number 1. Go ahead and whip out your guess method. You start this, and then we'll work it together. We have a 16-kilogram canoe moving to the left at 12.5 meters per second. Makes an elastic head-on collision with a 14-kilogram raft moving to the right at 16 meters per second. So after the collision, the raft moves to the left at 14.4 meters per second. Find the velocity of the canoe after the collision. This is going to take our guess method so that we're able to properly label which variable goes with what piece of information. Now, first things first, let's use our first step of the guess method, which is your letter G. For a given, my problem says I have a 16-kilogram canoe. That's going to be the mass of my first object, 16 kilograms. That's moving to the left at 12.5 meters per second. For me, I make everything moving to the left negative. So that's my first velocity. It's my initial. Moving to the left, it's a negative 12.5 meters per second. It makes an elastic collision with a 14 kilogram. This is my second mass object. That is moving to the right at 16 meters per second. Velocity of the second object, it's the initial, that was moving at 16 meters per second. Now, after the collision, the raft moves to the left at 14.4 meters. Remember, 16 kilograms was your canoe. The 14 kilograms was my raft. So, I've now been given that the raft moves to the left, which is always negative. So that's going to be my V2 final negative 14.4 meters per second. Find the velocity of the canoe after the collision. So our unknown will actually be V1 final. We want to know what was the velocity of the canoe. So our M1 was our canoe. The mass of your canoe was 16 kilograms. The velocity, the initial velocity of the canoe was 12.5. It's negative because it's moving to the left. The second mass we were given was for the raft, which was 14 kilograms. Its initial velocity was 16 meters per second to the right, which is why that number remained positive. It was then a collision, and the raft began to move to the left at 14.4 meters per second. It's negative because of the direction that it's moving in, all right? And our unknown is the final velocity of your canoe. Our equation is your conservation of momentum equation, because what we start with, we're going to end with. So M1 times V1 initial plus M2 times V2 initial equals M1 times V1 final plus M2 times V2 final. We're going to double check for our substitution step to ensure that all of our units are complete. So far, we're looking good. So let's combine, substitute, and solve, and plug in our numbers. Our M1 is 16. Our initial velocity is negative 12.5. Our M2 is 14. And our initial velocity was 16. Mass, again, of my first object, 16. We are looking for V1F. That's actually your unknown. So we want to find V1F as our unknown. We have our mass of the second object, which is 14. And after the collision, your velocity was negative 14.4. M1, VI for your first object. M2, VI for your second object. There was a collision that took place. My mass did not change. This is your unknown. Mass of your raft is still the same. Now the raft is traveling in a different direction. Grab your calculators and let's see what we can do. We're going to go step by step. First step, let's say 16 times negative 12.5. And I come out with negative 200. Plus 14 times 16 is 224. We have 16, and we still have our same variable. And then we're going to simplify here on the end with 14 times negative 14.4, which will give us a negative 201.6. Now, we want to get our variable, our unknown, by itself. So let's move this one first. We're going to simplify here. So negative 200 plus 224 will give you, you got it, 24. This is still our unknown. And we're going to simplify here and just put minus 201.6. Now, let's get ready to move this. We're going to do the opposite of what is already taking place. So we're going to add this to both sides. What's going to happen here? Those cancel out. I now have 16 V initial, V1, sorry, final. We love to say V initial. And This will come out to 225.6. Now, this is your trickiest step. Whatever number is next to the variable or your unknown is what needs to move. So we're going to divide, do the opposite, both sides by 16. We now have 225.6 divided by 16. My final answer is 14.1 meters per second. Be my final velocity of my first object. So let's revisit, see what we have. We started with the mass of your canoe and the mass of the raft. They were both traveling in opposite directions. The canoe was going to the left and your raft was going to the right. There was a collision that now forced your raft to travel to the left. We wanted to find out what was the final velocity of your canoe when everything was said and done. We went through and we used our conservation of momentum or elastic collision equation because we know whatever we start with, we're going to end with. And we traveled through and we realized the raft was traveling at negative 14.4, and guess what? These answers were pretty similar at 14.1 meters per second. These problems will often start out and appear really, really long. What you're looking for and what you're trying to ensure is that all of your variables that are necessary have been added in. If you start working your equation and you realize you have more than one unknown variable, you probably missed words such as stationary, rest, or constant. So be very mindful of those words that could actually represent numbers as well. Before you go, check out this other YouTube video. It does a really great job of explaining and comparing elastic and your inelastic collisions. As always, if you need me, feel free to email me. I'll see you guys in class.